Is about this talk is about room temperature ionic liquids. This is an area that many of you will know many things about, and I know some of you know a lot about. But I'm going to start, as usual, with an introduction for those of you who may not know much. It's a huge topic. I can't give a proper introduction. I'll give a crude introduction. I'll start with talking about aqueous solutions at charged surfaces. So words like EDL, electric double layer, are commonly used. And the idea is there's if you have an electrode or a charged solid surface, you have, of course, a charge in the solid, and you have the opposite charge in the liquid. The question is, how is that charge distributed? And that's relevant to all kinds of things. Corrosion and soil chemistry, of course, batteries, okay? Colloid stability, you need colloid droplets to be surrounded by ions, all kinds of things. Wet solid interfaces are very common. And so, of course, this is an old topic. It's not something new as far as aqueous solutions are concerned. And the problem has been to explain the capacitance of such a system. Why capacitance? You know, capacitance is like if you work on floating monolayers, you measure isotherms, and isotherms tell you relatively little about the nanoscale, but they're something you can measure relatively easily, and then you need to explain it. Then you need to do other experiments. So the isotherm is your canary in the coal mine. And in this case, the capacitance of a solid liquid interface is a macroscopic measurement that tells you something about structure. And this is of course history, that if you say, well, there's a interface and there's just one layer of ions along the interface, then you have a parallel plate capacitor, and the capacitance should be a constant. The distance is whatever it is. So just one layer doesn't explain the data. So you have to have a more complicated model to explain the data. And Gouy-Chapman involved a diffuse interface. And then Stern said, okay, you have both. My pen doesn't seem to be behaving. I'll switch to another one. Here we go. Okay, so Stern said, okay, put in a layer right next to the interface, but also a diffuse layer. And so when you make the model more and more complicated, it becomes easier to fit data, as we know in many systems. And so this is now more or less well established. But the aqueous solution of ions with ions in aqueous solution system is, well, the assumption made is that it's a dilute solution, that you neglect interactions between the ions. You just have the water be some featureless jelly, and it more or less works until you get to very concentrated solutions. Well, molten salts would be a different limit. So if you take sodium chloride and melt it, then there's no water in there. And all you have is sodium and chlorine ions running around. And then there's no reason the Gouy-Chapman-Stern picture should apply. And you say, well, that's quite different. It may be different. It may make better batteries. It may make weird batteries. It may make weird capacitors. Who knows? But the problem is, of course, that sodium chloride has to be heated up quite a bit. So making a pure soup of ions with normal salt, you know, an inorganic atomic salt, is not terribly convenient. But we do have a different system which has its own advantages and disadvantages. These are molecular salts, and that's what this talk is about. You use molecules, and they're liquid even at room temperature. They're these irregular, weird molecules. They make all kinds. There's something like 1 billion different combinations of molecules that make ionic liquids, and they're all kind of, well, ugly, if you like, because, okay, sodium, chlorine, as a physicist, we like those things. They're like spherical cows, you know. You can approximate them as point particles or certainly spheres, but these typically are not approximatable that way. They're certainly they're large, and you can maybe put ellipses through them or something. My pen works every time I test it. It just doesn't work in real life. There we go. Okay, so there are many ways of making anions and cations, and you combine them when you get these room temperature ionic liquids. Okay, so again, capacitance. Well, capacitance could be important if you need to store charge. You know, you have solar panels in the day, and you at night you need electricity. You need to store charge. You need a DC charge storage, and if you can make very large capacitors, that could be practical. But in particular, capacitance is used because A, it's easy to measure, and B, it tells you something about the interface. The thing is, it gets complicated. So I'll talk even more about capacitance in a minute, but certainly these liquids have a high ion concentration. The cations and anions don't have the same shapes. They don't have the same size. So you get this advantage of the liquid is liquid at room temperature, but you get these other complications that make these challenging systems. Okay, I've said that already. So experimentally, capacitances tend to have all kinds. You know, you take different ions, different RTILs, room temperature ionic liquids, and you often get these double hump shapes. And you can explain it with Kornyshev type theory. Kornyshev basically said, oh, here we go. I have a comment on this. What is capacitance? Okay. That seems obvious, but it's not at all clear. Different people mean different things by capacitance. Okay. The typical experiment is an AC experiment with a DC voltage offset. Okay. So if you have a capacitor where charge versus voltage goes something like that, then if you have some voltage offset and you're measuring a small AC capacitance over here, you're measuring dq dV, you're measuring the slope, okay? That depends on V, as you see in these pictures, but it also depends on frequency, and that's something that's not such a strong effect in ions and water, because the ions in water are relatively free to move. But these large, sluggish, ugly molecules, they're long dynamic effects, and therefore the different frequencies, you're going to get different capacitance. Then the other definition of capacitance might be Q over V rather than dQ dV, and that would be relevant for charge storage, which I was just talking about, and that turns out that that's what we measure with X-ray reflectivity. So that's a different number. So these are all dQ dV as a function of V, and what we'll measure is different. But these are weird shapes. This is not something you see in aqueous solutions. And there are ways to explain it by assuming vacancies, empty spaces in this lattice model of an RTIL, but I won't get too much into that. It's just the point I'm making is that these do behave differently, as you'd expect. They do behave differently from the dilute aqueous solutions. Okay, I don't need this slide. I said I would introduce the topic, but I will skip this unless somebody asks me what X-ray reflectivity is. The experiment we're doing is to go into an interface. Okay, we use silicon surfaces for reasons I'll explain in a minute, with the silicon with the oxide layer stripped off. So this is the RTIL. And the expanded picture, we're going to talk about solvent. So that's in the general case, there's solvent, there's anions, and there's cations. And the idea is what's happening at the interface? What is the capacitance due to? And what is the general physics of structure at the interface? Okay. So let me go back to some early X-ray studies. These studies from Metzger et al. Were done with a sapphire surface. Sapphire, as you fully realize, is not conducting, so you can't use the exact scheme that I showed a minute ago. But when it's exposed to X-rays, it develops a positive charge. It's estimated to be about 0.5 volt. And so as a function of temperature, particularly at lower temperatures, they found this minimum. Notice the minimum is at about 0.8 something. I'll come back to that point, but this is something like the size of the anions and cations. And so the data can be fitted with a model of alternating layers of anions and cations. And indeed, there's molecular dynamics and theoretical predictions that there should be these alternating layers. Okay. But if you're asking about capacitance, the question is, what's the net charge? And so with this plus and minus, you have to add it all up and say how much charge is there in here. And it's a small amount. It can be calculated. I don't have the number. It's a relatively small amount of charge at the interface at 0.5 volt or whatever the sapphire surface charge is. What we were interested in is the voltage dependence. Okay, and so you can do, the voltammogram, the current potential things. These are, I hope you've seen pictures like this. Once you get to large enough voltage, you're frying the system, you're cooking it, you're causing electrolysis. So you don't want to go that high. This is the material we've been studying, and it happens to have a very large electrochemical window. Okay, there's from here to here, you can say, well, there's no cooking going on. Okay, so we studied the structure in this range, and it turns out that low voltages like 0.5 volt and high voltages like 2 point something are quite different. Okay, again, that's not something you expect in aqueous solutions. Until you have electrolysis, it's all the same thing, but it turns out it's quite different. And this is from Miyaoki Chu and people in my group from 2016. I also added, as I was joking before the talk started, Rizal et al. From 2015, who also did X-rays from RTILs, but I'm not going to talk about that in this talk. Okay. So before I show that data, I want to show the RTIL we spend most of our time on. It has a smallish anion and a large cation. And here's a table. You don't have to look at all the numbers, but basically the anion is quite electron dense, which is, of course, why we and others chose it to do X-rays with, because you need a difference between the electron density and of one ion versus another, because otherwise they all look the same. Organic molecules have this problem that they're all the same. X-ray densities, sorry, electron densities, but these, they have things like fluorine and sulfur in them. So this is a small ion with a higher density. Okay, this is NTF2, and this is the cation. Okay. Now, one of the early papers on, just since we're talking to an X-ray synchrotron audience, one of the early papers doing reflectivity looked at RTILs against a gold electrode. And of course, gold is a nice thing. It's non-reactive. You can make fairly flat surfaces. But there's a problem. The problem is that the electron density of gold is awfully high. Okay. The result is any order next to a gold surface is just very hard to see. It just contrast due to layering or anything like that. It just doesn't show up against the strong density of gold. Well, silicon is not as commonly used as an electrode, but its density is not that different from the anion cation, or this pair by pair, we mean the bulk liquid. Okay, this is the bulk liquid. And so silicon gives you much less contrast and allows you to see the contrast when you have a separation between ions in the liquid itself as structure develops. So sapphire is the same way. It's not gold. Amit Duisel et al. Used, I believe, graphene, and that's of course good. Graphene's great. Gold would not be so good. So here's some data. And the first thing I want you to notice is that the minima we're talking about are at a much lower Q, okay, 0.1, 0.2. And what you can see is that at that Q, we don't see anything at 0.5 volt and 1 volt and 1.5 volt, 1.6 here and so forth. But then we start developing this smaller Q structure, which of course means a larger real space distance. And so if you fit it, we found it's perfect, you know, X-ray reflectivity fitting is of course a bit of a black art. We hate to introduce any more parameters than we have to, any more complicated a model than is absolutely necessary. And structures like this can be fitted using one slab, and occasionally you need a second slab. But basically what we see is a layer forming at the interface, this blue stuff here, that is getting bigger and bigger and bigger as you get to larger voltages. Okay? So what's happening? What is this layer that's much bigger than the size of an anion or a cation? Well, it had already been predicted, and the idea is it's a crowded layer. Okay, what's a crowded layer? Basically, unlike the Helmholtz layer, where you have a one layer of ions that can balance the charge on the electrode, here, because these molecules are large, these anions and cations are large, one layer isn't going to do it. And so you have a pileup, you have a traffic jam, you have all these ions collecting here, which of course completely changes the physics. It's not a parallel plate capacitor with a specific distance. It's a range of distances. And as you increase the voltage, the thickness of this pileup gets bigger and bigger and bigger. Okay, so that's your crowded layer, and it only happens at large enough voltages. Okay, here, if we went to higher Q, presumably there would be that minimum we saw in the Metzger et al. Paper, but we were interested in the low Q data. And you can analyze the data to get the thickness. Here's the thickness as a function of voltage. There seems to be a threshold. Okay, if you extrapolate it back, there seems to be a threshold. You can basically take this and say, what's the density as a fraction of the bulk IL density. So here, rho IL is the bulk RTIL density, the ionic liquid, and that ratio -1 is the excess density, and that seems to be more or less flat. And from that, you can calculate the surface charge density, and the slope of this is the DC differential capacitance, okay? So this is the charge, this is Q versus V. This is, of course, it's sigma because it's per unit area, but so this would give you the capacitance, but this would give you the differential capacitance at 0 frequency, which in turn is different from a 0 differential capacitance at some other frequency, which is different from the differential capacitance at another frequency, and so forth. But of course, because of the time scales involved in X-ray reflectivity, we're limited to long time scales, so static experiments relevant to batteries or DC storage. Here's what's interesting. If you look at this slope, it's about an order of magnitude higher than the AC capacitances, okay? You remember my showing you the double humped pictures, and of course those numbers vary with the particular liquid used, they vary with the voltage, but ballpark they're 10, 20, 30 microfarads per, this is a microfarad, of course, per centimeter squared. But if you look at this number, it's 10 times as much, okay? How do we get this number? Just to be clear, I'm sure you've already figured it out, but just to be clear, we're not measuring charge. We're looking at the density. We're looking at the fact that you have a higher density at the interface, and that density means you have more anions and fewer cations, since these are more dense. And from that, you can calculate how many anions, how many cations. Here's another interesting thing. If you imagine a complete, I just said, oh, there's a traffic jam. All the anions have crowded onto here, but they can't all get close to the electrode. This is the 0 is the electrode surface. They can't all get right next to the electrode, so they piled up here. That picture wasn't completely correct, because if you look at the actual density from the fitting of the reflectivity data, you find that the density is significantly lower than you'd expect for a mass of anions. So in fact, there are cations in there. So as a number ratio, there's something like 4 anions to a cation. See, that's a charge ratio, 4 anions to a cation. So even in this crowded layer, there's a mixture. It's obviously there's some net charge, but that charge is not as high as it could be. It's one of the many things we don't understand about the RTIL is in a simple picture, oh, they're all anions, but in fact, they're not. Of course, you can give a superficial explanation. You can say, oh, entropy, there should be some cations, but yes, that's the best I can do, to say that there's that's why there's a mixture of anions and cations, because the cations are so much larger. Remember, they're so much larger. In terms of volume, it's closer to 1 to 1. Okay, so but in terms of charge or number, it's something like 4 to 1. Okay, so this layer is something not predicted by theoretical analysis. Is not purely a single charge. At the same time, the charge as calculated from the density is much higher. Again, emphasizing that we're measuring a different thing from the simple experiments, the desktop experiments that measure AC capacitance. It's a lot higher. So maybe for storage of solar cell output at night or something like that, maybe RTILs would be better than one thinks. Okay, it's not been fully explored. Well, more recently, and I'm going to show you more data and say we don't understand it. So I know we have an expert audience who will help us understand this data. We've been looking at solvents, okay, RTILs dissolved in molecular solvents. And again, we're not the first to do this. I'll cite some references. But the two solvents we've looked at, kind of familiar solvents, are propylene carbonate, which happens to be polar, and dimethyl carbonate, which happens to be non-polar. They both dissolve RTILs anyway. Why would we want to dilute them? Well, just to see what's going on, of course, but one argument might be to see if one can make the transition from this dense soup to something more like the familiar ions in water system. Another might be to say, can we get it to a point where the dynamics are not so limiting? You know, the molecules are very sluggish. We and others have measured the time scales, and I'm not going to talk about the details, but in some sense, whatever your experimental time scales are, you see something happening with that time scale. Okay, things are very slow with many different time scales, and that makes it a problem to imagine using this in devices. So maybe dissolving them will improve the response, how fast the ions move. But we haven't gotten there yet. What I'm talking about now is what happens to the crowded interface structure when you introduce solvents. Okay, so you're diluting them, you're separating the ions by whatever distance, depending on how many ions and how much of the solvent. Okay, so there's a landmark work, several papers by Susan Perkins' group, where they measured forces in a surface force apparatus. This thing, the two plates go various distances, and did it as a function of concentration. Okay, so with a solvent. And this is, here's the material. The solvent is one of the ones we studied, propylene carbonate. This is the polar solvent. And they saw something spectacular, I suppose, that at higher concentrations, okay, so this is what you'd expect. This is your Debye length as a function of concentration in, let's say, an aqueous solution. Okay, what you'd expect and what the Debye-Huckel theory predicts is that the decay length, okay, the Debye length, for example, the Debye length measures how far an electrostatic influence goes, how far the influence of a charged particle goes into the liquid or a charged surface. Okay, and so the higher the concentration, the more you'd expect it to be neutralized by ions. And so when you have a dilute solution, you have a high decay length or Debye length, and as you get it more concentrated, it becomes smaller and smaller. Okay, well, that's not what they see. So the line is the theory. There are two lines, and I won't get into the difference between them. There's a dotted line and a solid line, and they're basically the same. And there's no lack of experiments confirming the shape of this curve in the dilute limit. But what they saw in the concentrated limit, more RTIL, is that the length went up again. Okay, so this was the core, this phenomenon is the core of this controversy from some years ago. I don't even have the reference, Israelashvili and others, saying that RTILs are not actually a soup of ions running around. most of them are bound together, and they're maybe polar, but they're not free ions. But that comes from here. You say, well, that's actually not here. It's actually here because most of the RTIL is just a neutral solvent. Well, that's one explanation for this, but it doesn't really explain why, as you add solvent, it becomes less concentrated. It comes down here and then goes back up again. Okay, and Perkin also studied, this is what, sodium chloride, and found the same thing. Yes, sodium chloride, and found the same tendency. It goes up at high concentrations where you expect, okay, the theories to fail. Indeed, it fails. It goes right back up. Okay, turns out, I won't get into too many details, but it turns out if you scale it by the size of the ion, then these curve, the blue and red curves, and they all fall together on the same picture. Okay. So this is in this picture, this is 1 because they've divided lambda experiment by lambda d. So again, what they're measuring is the force as a function of distance and finding the decay length. And the decay length is the Debye length, but then it starts deviating from the Debye length, which is what you see here. Okay. What's going on? Well, we don't know. Okay, and we didn't do this experiment. This is just background. But another theoretical explanation was that from Perkin et al. Was that, when you're up here, when you have a very concentrated solution, what you have to do is treat the solvent as the charged particles. I don't fully understand it, so I won't talk about it. But anyway, it's a mystery. It's a bit of a strange phenomenon that our data does not directly test, but what I'll show you is something somewhat similar to it. Okay, so this is the same ionic liquid dissolved in PC, the same liquid that the Perkin data from a minute ago was used, the polar solvent, and these are different concentrations. Okay, so when you have a lower concentration, a very dilute solution of ionic liquid, you do get the pileup, the crowded layer, but it's both less dense, okay, less dense and less thick. Okay. And there's continuously, you can see these peaks move. You continuously go from the pure ionic liquid to the very dilute liquid, and the things are getting thinner, and of course they're getting less dense at the same time. What's going on? Well, we don't fully understand the crowded layer, so it's not surprising that we don't fully understand how it depends on solvent concentration. Again, please feel free to interrupt, okay? But one can wave one's hands, and I'm going to, okay? What we're seeing is not the same as what Perkin et al. Reported, but somewhat analogous to it. When you have, okay, so what we have here is that we're not measuring a pure Debye length, obviously. But what we have here is that the influence, the electrostatic influence of the electrode, which is this, the red part here, it goes further. Even when the ions are piled up here, attracted and forming a crowded layer, it goes further. When you have a dilute solution, it actually doesn't go as far. The obviously here you'd have electric field equals 0 out here, okay? Because if it were not, it would attract more ions. But the point at which the electric field goes to zero with this pileup, with this crowding, is further away with the pure ionic liquid compared to the solution. Why is that? It's specifically counterintuitive because you expect that if you have more ions, they will screen the electrode charge, the electric field more efficiently, but in fact, it does not. These don't screen the electric field. You have to go further and further away, and there's still these charges are trying to get to the surface. So qualitatively, it's a similar phenomenon. It's a counterintuitive phenomenon. It's counterintuitive if you're used to the dilute aqueous solutions. On the other hand, there's no way you can say that, oh, these these RTILs are not really charged. They're just molecules with the cation and anion bound together. So they're the reason I said back here that the one explanation floated for these large Debye lengths is that, oh, the RTIL is really a neutral solution, maybe a polar solvent, but it's a neutral solution, and that's why there's very few ions in it. Well, you can't make that argument here because it's about 80% anions and 20% cations. Okay, so 20% of the cations could possibly be eliminating 20% of the anions, but that still remains 60% to neutralize, to be charged. And yet these charged particles are not neutralizing the electric field. It's called and the way we know that is that this pileup is much longer. Again, just to point out, these things are at low Q. So we're talking about a much longer length than the sizes of the anions and cations themselves. Not much longer, but significantly longer. They're not much longer here, but much even more long here. So it's hard for us to explain, okay? This shows, this was of course at a high voltage, 2.5 volts, but we did it as a function of voltage. This is for PC, the polar solvent. This is for DMC, the non-polar solvent. And there's a bit of noise here, but this is the layer thickness as a function of volts. And these lines are connected just to help you see it. And more or less, you can see that the layer thickness increases with voltage, and it decreases when you have a more dilute solution. This is dilute, this is concentrated, this is 100% IL over here, 100% IL over here. The differences between the polar solvent and the non-polar solvent are small. But the polar solvent seems to have fewer cations in the bulk layer. And indeed, there's a simulation paper. I didn't put the citation up, but I have it here for anybody who wants it, that suggests that if you have a polar solvent, you know, I would like, being simple-minded, I would like to have a nice, elegant electrostatics explanation that says, oh yes, polar molecules do this. But no, it's not so simple. It turns out that if simulations have been done and confirm that in the PC layer, you'll have less cations. This data doesn't show it, of course. This is just the thickness, not the density, but it's going to have less cations than the non-polar solvent. But it's a small effect. It's more or less something like, you know, 75-25 or 80-20 anions to cations. It's never 100% anions, and the thickness goes down as you dilute it. which is pretty strange. So here's another way to slice the same data. And this will require a little bit of an explanation. What you're seeing here is, this is raw data. It's excess electron density. It hasn't been interpreted in terms of the charges and how many anions and how many cations. It's just how much the electron density of that crowded layer, the layer near the interface, exceeds the electron density of the bulk. Okay, so when it's this here at 100% is the data you saw earlier, and it exceeds it by some amount. And as you dilute it, there's almost a linear relationship going to zero. If I'll come back to these points later, but here there's a linear relationship, which is consistent with saying everything is diluted by the solvent. Okay, if you have half as much ionic liquid in the bulk, you have half as much ionic liquid in the pile-up layer. Okay, so that's a reasonable assumption. Down here, it starts deviating. Okay. You will see the similarity with this picture. Okay, although we can't really go to these small distances. And the reason we can't go to these small distances is because when the ionic liquid is dilute, of course, it's pretty dilute, and the contrast gets smaller and smaller. And at some point we lose it. We'd love to go up here, but we can't. All right. This is the same data processed to look at the excess of anions over bulk. So again, here, this is bulk. My handwriting, never very good, fails when I have to write on a screen. So in bulk, you have this is per nanometer. These numbers don't mean anything. It's not going to 1, it's going to the number of anions per nanometer cubed, which happens to be close to 1. So as, of course, you dilute the system, you'll have fewer and fewer anions. And indeed, when you have 0 RTILs, you'll get 0. Okay? So this is the crowded layer. And when you get here, you get the same thing. The number of anions goes down. The ratio of anions to cations remains the same. The number of anions goes down, and there's this deviation down here. Okay? So for a large range of reasonably concentrated, 40% ionic liquid or more, what we find is that that the density just shrinks, as though it's the ratio of solvent to solution, solvent to IL is the same in the crowded layer as in the bulk. But down here, you start to see a deviation. Okay, so you can look at it and take the density. You can take the width of the layer and calculate the excess surface charge. You saw earlier in the older paper, this is all unpublished data. In the earlier paper, you saw the data for pure RTILs. We can now do the same for solutions. And you find that the capacitance actually drops. You don't help the system by making it more dilute. But the maximum surface charge is actually not for the pure material, but for just a little bit of dilution. Okay? Of course, that's only 1 point, but it turns out that these capacitance measurements that I've been talking about, and I'm saying, oh, completely different. The capacitance measurements show a very similar effect as a function of dilution, is that there's a maximum. Do we understand why? We do not. When I say we, I mean I do not. Okay, but there's a small amount of solvent will actually increase the interface capacity. Remember, again, we're looking at this DC capacitance, the total surface charge versus voltage, whereas they're looking at the AC capacitance, and I don't even remember the frequency involved there, but there's a peak. This is PC here on top, and this is DMC, and DMC, we don't see a peak, okay? So what's happening here? Well, there's one of the many things we don't know, going back to the double humped form of the capacitance that people measure. We can't go to the other hump, because if you change the sign of the charge, of course, instead of, if I can go back to here, instead of anions, you attract cations, and cations don't have any contrast with the bulk, okay? The difference between this density and the bulk density is much smaller. And so unfortunately, it's not easy to look to change the sign of the charge, the voltage on the electrode. But when you have the anions at the interface, there's a large contrast difference between that and the bulk, so we can measure it. But so the double humped capacitance picture that I showed you, here, see, that's theory and experiments. This is at different two humps at different sides. We can't do both, but we see one hump here. Okay. Wait. Just to make clear, in order to go from the excess density, which just comes from a one slab fit, to the number of anions, we have to assume that the solvent concentration is the same in the crowded layer and in the bulk, because otherwise there are too many parameters and you can't fit it. But this line here confirms that that's a reasonable assumption. And then we can calculate the number of anions. It's about twice that in the bulk, but it's never, anion concentration is twice that in the bulk. But because the anions are so small, they really could have been 100% and have a very large amount of charge, but they don't do that. There's always some cations mixed in. Okay, I left out a certain amount of very interesting data on time dependencies. So I find that I've run out of time, I've run out of slides a little early, so let me summarize. I tried to write a summary, and I wasn't really sure how one summarizes this, okay? So I'm going to leave it to the expert audience to see if you have any comments on what the physics is behind these counterintuitive behaviors. And so I'll just say that RTILs are very strange, and thank you for your attention. Nobody ever interrupted me, but now's the time, please.
Okay, thanks, Pulak.